I think it's more like I have this entire cloud is pretty You just text me.
Okay, everyone, let's start. I want to make sure that we can finish hierarchical clustering and start our DB scan. I want to see the energy over there. Okay. Good afternoon, everyone. Good afternoon. There you go. Okay. So, what do we have our students? You're going to have what this Friday? What is it that you have that you need to submit? Project proposal. Okay, so I'm going to talk about 1 or 2 minutes about project proposal, and this is something very important. Okay, so when it comes to project in general, and because we are human, what happens? Something called conflict, and unfortunately that happens sometimes or often, so conflicts, or sometimes I call it also friction among team members. And why this conflict happens? Because they're not communicating well. Because some of team members are pulling all the weight, and the others are just kind of like have a good ride, the whole process. Okay, so I want to make sure that whatever that you have kind of in your capacity, make sure like any type of communication, is it going to be MS Teams? Is it going to be calling? Is it going to be text message? It's going to be WhatsApp, whatever you have. Make sure that you communicate with your team constantly. That's quite important. If they're not a part of team, okay, and I'm just telling everyone to make sure that we understand that, we have something called peer evaluation. If you're not contributing the same as the others, we don't, like the people who are doing well, that's fine, they're going to get the grades, but others, we're going to give you 0, even it can go to 0. And project is like, what is the percentage of project for us? 20, 25% of your grade, it's just going to create a lot of problems for you, okay? So be careful about that. Be careful that you work with your team members, and that's what I want. It's not just about just doing some ML project. For us, it's mainly about social skills, how you can work in a context of group, and how can you achieve something good, okay? Any question about project or anything that you would like to ask? No, good? Okay. So let's go back to our lectures. Hierarchical clustering. Okay. So when we started talking about hierarchical clustering, I mentioned this algorithm is we construct a tree-based structure, and I said that don't call it tree. It's like, this is not what we call it. We should call it what? Dendrogram. So we were trying to create something called dendrogram. And this algorithm, hierarchical clustering, is it soft clustering or hard clustering? Hard clustering. Okay, so all algorithms that we teach here in our class, except one of them, which is soft clustering. Which one was soft clustering? GMM. Just GMM was soft clustering. The rest of them are hard clustering. Okay. And so I created this dendrogram, and I mentioned that one. There was a kind of a main constraint or main limitation or problem with k-means and GMM. And that was the reason we wanted to use hierarchical clustering. What was the main reason that I wanted to use hierarchical clustering? Yes. The number of k's in advance. So I needed to know those pre-decision. I needed to know those in advance. In hierarchical clustering, we know it when? Post-decision making, which means that we come up with this dendrogram, then we cut the dendrogram. Okay, we cut this dendrogram. Okay, in order to create your dendrogram, we have a bunch of links. I mentioned how to merge some of these clusters. Single link was the shortest of the shortest, remember I mentioned. Complete link was the shortest of the what? Longest. And then we had centroid, which means that I need to calculate the center point in my clusters and connect those together. So I have this distance, which we call it centroid link. The other one is called average link, where I calculate all these distances and then calculate the average. Good? Good. Any question about this part? So if there is no question, let's pass these. I'm going to give you one good motivation why we use hierarchical clustering. So this is one example for the facial kind of position. If you look at here, at first we have all these clusters, and if we go top to the hierarchy, it tells us, like for instance, these faces will facing right, these are facing center, and these are facing left. And when I go up here, so you can see all these kind of positional, and that can be essentially very good algorithm, especially if you have visual representation. Okay, let's have it here, single link and complete link. Let's solve this one. Who wants to help me? You got to use this pen. Want to help? Okay. What was your name?
Michael.
Michael. There you go, Michael. Let's see if I have, what color do you like, Michael? I love purple too. So we're on the same page. Okay, so for single link, at first, how many data points I have? 8. So this means that how many clusters we have?
Currently 8.
8. So why not draw a small circle around all of them, so that represents a cluster? There you go. Wow, that's just a background noise. That's good for us. Okay. And now if you were to merge one with any other cluster, let's say 1 with 2 with 5 and so on, which one you would merge one with? Well, first, because this is the first step of the algorithm, we don't really care about the links. Okay? So which one are you going to merge one with?
You merge 1 with 2.
2, okay, so draw another kind of like a, there you go. So the same goes for possibly 3 and?
4.
The same goes for?
5, 6.
Okay, 7. Why not calling the first one, the first cluster A, second one B, so C and D, so we recognize them later on. So if you were to merge A with C, single link means what? The shortest of the?
Shortest.
Okay, so what is the distance from A to C?
It'd be the distance from 2 to 5.
Why not draw a line? Oh, let's connect 2 to 5. Oh, no, the dot 2 to dot 5. We can do it. Well, there are a lot of artifacts over there. You can use back of your pen to remove, it works like a back of your pen.
Oh.
This is what is suffering I go through, you know, you can see it right now. Okay, there you go. How about A to D?
A to D would be 2 to 7.
You got it. How about A to B?
Either 1 to 3 or 2.
Because we started with 2, why not doing 2? So it becomes 2 to 4. So among all these, which one is the shortest one?
A to C.
So why not merge A with
C.
There you go. And the same goes for B and D. And the last one is what?
All of them.
All of them together. Okay. Do you want to help us with complete link as well?
Again.
Thank you. So at first, how many clusters do we have?
Still 8.
So draw a small circle. Okay. So if you, at first, we don't really care about the links, the type of links we use. So which ones you're going to merge?
For the first one,
For the first one, 1.
you can, if you're doing complete link, would you not want to merge the farthest ones?
Yeah, but when the cluster has one single member, that's the time we don't really care whether we are complete or single or average or anything.
Okay, so you would still just go ahead and merge like 1, 2.
The closest one, which is what?
1 and 2, and then 3 and 4.
Uh-huh.
and then 5 and 6, and then 7 and 8.
Let's assign a number, name for each cluster. Okay, so because we're using complete link means what? The shortest of the farthest. Okay, so what is the distance from A to C if we want to use complete link?
1 to 6,
There you go. How about A to D?
1 to 8,
Uh-huh. How about A to B?
and 1 to 4.
Let's remove the other one so it doesn't confuse us. There you go. So among all these, which one is the shortest?
1 to, or A to B.
Exactly, so let's merge them then.
And then you have the same thing for C to D.
Yep. And then the last one?
Is all of them.
You got it. Thank you, Michael. Okay, are we clear now? The way it works, complete link and single link. Okay, so if you remember, by the way, Michael, we had the answer, you did a good job, so good. Okay, so if you remember, I mentioned one of them has the tendency of creating chains, and the other one has a tendency of creating a kind of a balanced dendrogram. Anyone remembers which one chain, which one?
So, it was
Completely more balanced. Single link, yes, that's correct. Single link is for chain. So let me use this one, single link. Okay. So how many data points I have here in this example? 5, which means 5 clusters. Which one you would merge first? No, at first. What is the first one that you would merge? What is the distance from 1 to 2? 1.5. What is the distance from 3 to 4? Which one you go first?
3 and 4.
There you go. Thank you for changing your mind. Okay, what is the next one? 2, okay. And now what is the distance from A to B if you use single? 3, because it's 0.2 to 0.3. What is the distance from B to 5? 4. So which one I should merge? A and B. So you can see that this chain is happening and is absorbing everything. It's so hard to get rid of it, right? Because we're using single link. Okay, so now let's use complete here, complete link. So which 1, 2, 3, 4, and 5? Which one I need to merge first? 3 and 4, because the first step. Okay, next one? 1 and 2. So what is the distance from A to B? 5.5 means they point what to point what? To point 1 to 4, complete link, the farthest one, right? How about B to C?
4.
So which one is? 5. So which means A to B or B to C? Which one I should merge? Which one has a shorter distance? B to C. Are we getting rid of this chain right now? Are we breaking it? Now you can see that we are breaking that chain because of the complete link approach. And now we have it here. Okay, let me give you another example. Let's use single link here. And I'm going to say that these are all equidistant. Okay, so at first we have, I don't know how many data points we have that many clusters. Okay, so 1, 2, 3, 4, 5, 6, and 7. So which one you're going to merge? Why not 1 and 4? Doesn't matter. I can just pick randomly. So let's do 1 and 2. I'm going to call this one A. What is the distance from A to 3? How did he get up with like 1? Oh, so 3 minus 2, these are indexed. These are not values. Okay, so this is 2 to 3. Let's call it 2 to 3 because we don't know what the distance is. How about 4 to 5 is what? The same. Okay, so if I want to have kind of a chain structure because I'm trying to get to a point here, which one I should merge with? A with 3 or A with 4 and 5? A with 3. So this becomes here. Which one I should merge? Let me call this one 7 with, let's call this one, I don't know, AA. becomes 7 with AA, and then it becomes ugly soon. Let's say we consider everything here. Okay, so that's it. So which one is left alone? Center point. Okay, the center point. So let's look at it here, complete link. This becomes a little bit tricky, but I want your help. 1, 2, 3, 4, 5. So which one I need to merge? Doesn't matter, right? 1, 2, 2. Let me call this one A. What is the next one? What is the distance from A to 5? It becomes 1, 5. What is the distance? Which one? If I wanted to merge, so should I merge A with 5 or 3 with 4? Which one? Are we clear? Back there? Which part is confusing? Tell me.
Why would we merge to 4? 4 is so far away.
So, what is the distance from A to 5?
It's 1 to 5.
1 to 5. This is it, right? 1 to 5. Okay. So, what is the distance from 3 to 4?
Oh, 3 to 4.
Yeah.
I'm sorry. Oh, okay, it's just
So-
from 3 to 4.
Okay, 3. What is the distance from 5 to 6? 5 to 6, right? So now I can choose randomly, whatever I want. But let's say I'm going to go with 3 and 4. Okay, just randomly pick one of them instead of 5 and 6. Doesn't matter. Are we good?
Yeah.
Clear? Are we clear there? Anyone? Any question? Yes.
Did you also pick randomly to group 1 and 2?
Yes. That was random too. Okay. So this means that I'm going to have a group of pairs of all these points. Okay. If I call this one A, B, and C, let me call this one Z, D, and E. What is the distance from A to C? 1 to 6. What is the, okay. So if I want to merge A with B, C or Z, which one I should go with? What's that? Right. So, wow, this distance, which one is? Based on the number, maybe, which one do you think is larger value?
They should be the same value.
Sure.
Because you guys make it a triangle.
Okay, so if anything is wrong here, it's on you then, okay? So let's say I'm going to merge these two, okay? Merge these two. I'm going to call this one AA, and I'm going to call this one C and half. Okay, what is the distance from AA to Z? What's that?
So all the radius.
That's the radius, doesn't matter, right? What is the distance from AA to C? 4, 6. Okay, which one is a greater one? Or which one is the shorter one here?
4 to 6, but could be anything.
A and Z is a
Shorter.
shorter value, right? A and Z. So here, 1 and Z. So this means that now I'm going to just have this into this cluster. So we are breaking out of this chain. Yes.
How is the radius of the circle less than the distance between 2 points on the circle?
So this one is a 4 to 6. What is the value here?
It should be less than the radius of the circle because you're not at the, like,
So that the radius is going to be, we need to calculate it, but the whole idea is that we're going to get out of this chain much faster than
this one, yeah.
this one. That's the main idea. Okay, that's the main idea. Okay, yes.
What if you start grouping like B and C and then D and E first before getting the radius in?
Yeah, in fact, I need to do it. So I just jump ahead. You're right. I just jumped ahead. So what I need to do, I need to put these together And then once I get to that point, then I merge them, right? And then it becomes this one. Good? Okay, good point. Okay, so we're done with hierarchical clustering, and I'm going to introduce you a new clustering evaluation where we can use it for GMM, K-means, and also hierarchical clustering. What was the first clustering evaluation we learned in our previous class? Elbow is the first. In the previous lecture, what we learned? We learned silhouette coefficient. Remember that we had mu in, mu out, silhouette coefficient. So this one is quite similar, but we're going to understand how this one behaves. This is a different one. Okay, so we want intra-clusters, the data points within a cluster, to be very close to each other, and inter-clusters to be as far as possible from each other. Okay, so for this, we need to define two measurements. We need to calculate two measurements. First one is called cohesion. The other one is called separation. Cohesion means that the distance within the data points inside the same clusters. Okay, so if this one is A, this one is B, C, and D, the distance from A to B. Typically, what type of distance function we use? Euclidean. Right, that's our typical choice. I'm going to calculate plus A to C plus A to D plus B to A plus B to C plus B to D and so on. So how many times I counted the distance from A to B? Twice. Okay, that's why I have 1/2 here. When we do programming, and this is a mathematical expression, in reality, we don't want to calculate it 2 times because it takes time. When you calculate it using your program language, you want to count it. Okay, bless you. When I sum them up, it's just going to give me cohesion value. So I have a question here for you. By the way, this one, this value, the cohesion, do I want it to be a small value or a large value for good clustering? The data points within the same cluster must be very close to each other. Should be a very small value. Okay, so I have another question, and tell me what is kind of the loophole, the problem with this algorithm. If I have 4 data points within the cluster, just a second, if I have 4 data points within the cluster, and if I have 100 data points within that cluster, if I want to compare it, if I calculate cohesion for 4 data points, and if I calculate cohesion for 100 data points, which one is going to give me a large value? Which one? 100, because I need to calculate 100 distance and sum them up together. So this means that there is a problem with this algorithm. Right? So if I have more data points, it will lead to a larger value. So how can I solve it? What do I need to do? Yes. Can we divide and so what is this process called? No, in general, we need to, if you want to have a fair comparison, we need to normalize it. This is called normalization process. So what type of normalization people do? They use number of edges instead of number of data points. So how many edges do you see among 4 data points? 1, 2, 3, 4, 5, and 6 edges. So how do we calculate the number of edges? Anyone knows the equation? Anyone? Yes?
N is the number of data points that N
It's called what? N choose?
N choose 2.
There you go. That's it. And how do we write it? So what is the kind of the equation? This is a simple form that we can write it.
N times N minus 1 over 2.
You got it, over 2. So if N is equal to 4, this becomes what? 4 multiplied by 3 divided by 4. How many? 6 of them. Now I need to divide down and this value of cohesion divided down by total number of edges. So if I have 100 data points, I'm going to have more edges. So that's why the comparison is going to be a fair comparison now. So it's not going to be one of them super large, the other one is going to be super small. Okay. Are we clear about this? Are we clear? Yes.
The number of edges grows quadratically with the number of data points, but you're only dividing
Yes, again, so it can be a little bit problematic over there, but it works well in practice. It works well in practice. Okay, so the other one is called separation, the distance from one cluster to the other cluster. So if I have A, B, C, and D, the distance from A to the other one, A to the other one, and so on. And also we calculate the distance the other way around. And that's why we have 1/2. Okay, so we calculate all these distances, sum them up. How many data points I have in this cluster? 4. How many I have in this one? 4. If I have 2 different clusters, anyone knows how to calculate the number of edges? The number of data points in one of them multiplied by in the other one. So it becomes how many? So we're going to create 16 edges. That's how you calculate the number of edges for separation. So that's an example here. NN is, so if I have 3 data points, how many edges? 1, 2, n, which is n minus 1 divided down by 2. So this becomes 3. So if I have 2 data points here and 3 here, how many edges? 1, 2, 3, 4, 5, 6. How do we calculate it? 2 times 3. Okay. So we have a measurement which is called beta CV, Wn divided down by Nn. Do I want the numerator to be a large value or a small value for good clustering? Cohesion. I want the cohesion to be the normalized cohesion value. I want it to be a large value, small value. Small value. How about denominator, the separation? I want it to be a large or small value. I want clusters to be far from each other or close to each other? Far from each other. So what is a desirable value for this? Is large value or a small value? Beta CV. So the smaller the, yeah, smaller the better. Okay. Are we good? Any question? Yes.
Could you just go over the limits for the sums in NL?
The what?
The limits on the sums right now.
Oh, so those limits, like how it's working and so on, that's essentially like if I start. So you can put the numbers I and j, and k is the number of clusters. Then you would understand how it works. Just put the number of clusters over there. Let me also mention this one. This one's quite important. I have W, Ci, Ci. Let's say I have 3 clusters. W, C1, C1. Do you think this one is separation or cohesion? This one is R. The distance R, the distance within the same cluster. That's how we represent it. How about this one? This one is what? C1 to C2. Separation. Okay, so this one is cohesion. This one is. So we have it here. So there is another method which is called yes.
Sorry. Back in the formula, is the Ci bar representing just all other clusters?
Yes, I'll give you an example. That's kind of complementary, like there's C1 versus the other one.
Yep.
Okay, so the other one is called normalized cut, and the question was some of the drawbacks of using edges, and the question becomes, what if I can just only use distances to normalize the whole thing? Okay, I don't want to use edges. And for this, we're going to use this normalized cut. So how does it work? NC, let's say if k is equal to 3, it is separation divided down by cohesion plus separation. And that's how we calculate it. So what is separation? It's WC1 and what? No, just I have 3 clusters. Let's just expand it. C1 and C2. What else? Plus C1 and? Okay, plus C2 and? These are all the separations that we can have. Okay, how about denominator? What is the first cohesion? C1, C1. What is the second cohesion? And third one? This one is equal to our separation. Plus, I don't want to write it here, so it's plus separation. Okay, so numerator, separation. Separation. So numerator, separation. I want it to be a large value separation or small value? Large value. And so that's why normalized cut, the larger, the better. Okay, larger the better. So now you know 3 or maybe 4. Elbow method, second one what? Silhouette, third one, beta CV, last one, normalized cut. So when you do your unsupervised learning, I gave you 4. So you must do all of them for your project to understand how your clustering algorithm behaves. Okay. Any question? Yes.
For the separation, you wouldn't have to also compute WC2, comma C1, and WC3, comma C1. It's the same value, but you said that you're computing the same thing twice, right?
Yes. So we don't need to do it. Yeah. Because distance is what? Symmetrical. Right. If it was not, then we would have been in big trouble. Okay. Good. So this part is done. Let's go start our DB scan. So we're going to talk about density-based clustering. Yes.
So amongst the different clustering methods we've discussed, we understood why k-means was necessarily ideal for data sets that had specific shapes.
Between hierarchical clustering and GMM, which one? So hierarchical clustering is a very good algorithm when it comes to visualization, and we don't need to define the number of clusters in advance. But it comes with the price of being very computationally expensive. Because if I have 1 million data points, then I need to calculate this pairwise distance of 1 million data points. So typically, hierarchical clustering could be done for a small set of data points to understand how they behave. And that's what I would do for the hierarchical clustering. And there are also different shapes of hierarchical clustering. So this one is a dendrogram. This is a dendrogram, everyone. So what I use kind of a vertical dendrogram. Here, instead of having a horizontal cut, what type of cut I need to have? A circular cut, right? So if I have a cut here, a circular cut. And that's why you can be very creative when it comes to dendrogram. So that's one of the very good visualization that we have. And these type of, anyone is taking data and visual analytics? Have you taken that? No one? So these graphics, if you want to just come up with these graphics, there are some libraries that people use. Have you heard of D3? Anyone? Some of you. So you need to use JavaScript. And what is the worst language in our world?
JavaScript.
C is king when you compare it to Java. JavaScript doesn't have any rule, unfortunately. What is it? What is happening to that variable? Right? So that's a very hard language. So we don't like it, JavaScript. But the problem is that how many front-end language we have?
JavaScript.
That's it, just one. I mean, there are some frameworks around it and so on, but still one. For backend, we have Python, we have C, we have Java, we have everything. But JavaScript, we got to deal with it. And that's just a lot of things that for visualization comes to, and they are JavaScript-based. OK. Density-based clustering is quite interesting, but let's have the meme of the day. It's quite interesting meme here. Oh. When you're a constant and you see d over d of x. Okay, this is not something that we like in our machine learning class. If that happens, we're done. Okay, we just got to live the rest of our life, and then we don't want to deal with that for optimization, essentially. Okay. So before I start density-based clustering, I'm going to ask a very simple question here. So I have two centric clusters, okay? Let me make this one middle. I have these two. If I were to use k-means clustering, or I don't know, GMM, and if I have these two data points, what do you think is going to be the behavior of k-means? Anyone, any idea? If I use k-means, what do you think is going to be the behavior? How it's going to split it? Yeah. Top half. Because of what? Because of which part of k-means?
Euclidean distance.
Exactly, because of the Euclidean distance. So what's going to happen? It's going to split it into half this way. Oh, no, that's not the half. So this means that it doesn't understand what we call it density, local information. K-means and GMM, what they do, they just capture global information. They don't capture local information. So that's why we're going to talk about something called density-based clustering, which is called density-based spatial clustering of application with noise. And we put them together, we just call something called DB scan. Very famous algorithm out there. Very simple, works very well. It understands local information, so you can just apply it and you can give you awesome results here. Okay, so how it works. So one good advantage of this algorithm, we don't need to know the number of clusters in advance. Okay, it will give you the number of clusters at the end. Also, this one is a hard clustering algorithm. The only one that we have soft is GMM. But for this algorithm, we need to have two parameters predefined. One of them is called epsilon. The other one is called min PTS. So what we do in DBScan a lot is called radial search. We do a lot of radial search. Epsilon is just your radius value. What is the radius value? Min PTS, it says that how many data points I have within that epsilon neighborhood. Okay, so if you look at Q here, I'm just going to draw Q here. So if I consider this data point itself, I'm going to start from here. How many neighbors I have? 1, 2, 3, 4, 5, 6, 7. Let's say the center here is 8. Do you think this one satisfies these numbers? Yes, within that epsilon. So how many data points I have here? 7. So is it greater or equal than 5? Yes, this means that it satisfies this condition. How did I come up with min PTS 5 and epsilon 1? That's a question I need to answer later on. But in order to run this algorithm, you need to know min PTS and epsilon. Yes, this one satisfies this condition. I call this one a high density region. Let me give you another example here. Let me start with this. Anytime you do the counting, you got to consider the data point itself as well. Okay, so how many I have within this epsilon neighborhood? This is our epsilon. 1, the center is inside, 2, 3, 4, and 5. Does it satisfy this condition? Yes. It also satisfies the equality is a part of that condition. So if it satisfies this condition, we call this data point a core point. Okay, so by the way, DBScan is one of those lectures we love to ask a bunch of what type of questions. It has a lot of definitions into it and so on, which is perfect slides for quiz question. Okay, and I'm going to tell you that which part we're going to ask questions, so pay attention. This is important, as what is core, what is border, and so on. Okay. How about this point? Do you think this point is a core or border? Does it satisfy this condition or not? 1, 2, 3, 4, and 5. Let's say the center is inside. It does. So this becomes also a core point. How about this point? Do you think it satisfies the condition? No. But because this point previously was in the epsilon neighborhood of what? A core point, we call it a border point. Although this point is not core, but this point was in the epsilon neighborhood of a core point. How about this one? This one belongs to none of them. We call it outlier. So in DBScan, we're going to encounter 3 points: outlier, border, and core point. I'm going to show you an example here so we'll understand it very well. What is the benefit of having outlier? Anyone? Let's see if you have any other members. What is the good thing of having outlier? An algorithm that will give us really outliers. What is the benefit of that? Anyone? Any motivation do you think in your mind? Let's see if you have any other members. Maybe this side. Let me see if you have other members. Anyone? What is the benefit of having outlier? Fine, I'll go with you.
Does that maybe tell us that that point could either be, like, if it's not a part of any cluster, maybe it helps us identify if maybe that piece of data might be incorrect or...
So if you are going to work on a project, and then what could be one reason that you're going to use DBSCAN? For which part of your project, yes?
Use it to clean up data.
You were close to, for the pre-processing and cleaning up your data, right? DBSCAN is a very good algorithm in that sense, because it gives you outliers. It will give you outliers, so we can use it that way to explore your data, to understand your data. Okay. So let's see how it works. I have epsilon1, min PT as 5. And in order to run this algorithm, we need to start from any random point. Okay? So let's say I'm going to start from this point. What is the status of this point? Does it satisfy this condition? No. So should I say this point is visited or unvisited right now? It's visited. So if you have a queue data structure, and I'm going to say that this point is visited, I'm not going to look at this data point anymore. Okay? And I'm going to call this one outlier. Okay. So let's look at another data point in random. Let's say I drop it right here. Core, border, or an outlier? Why? How many neighbors? More than one. 1, 2, 3, 4, 5, 6, 7. So now what I need to do, out of this 7, how many of them are visited?
0.
One of them, this point is visited. Six of them are unvisited. So I'm going to put all these 7s into a queue data structure. Now we have 7 data points. One of them belongs to this high density region. Okay, now we need to take care of the other 7. We need to go and visit them, making sure that the labels from unvisited will change to visited. Okay. So how about, let's start from here. This point, does it belong to this cluster or not? No. Not yet. This point, is it a core point or border point? Because it satisfies this condition. Because it's a core point, I'm allowed to add the neighbor of a core point to our existing queue. Okay? So now our queue is getting what? Getting larger or not? So it's just being expanded. Okay, so I'm going to add it to our queue here. Good? Okay. How about this point?
Yes.
1, 2, 3, 4. What is it? It's hard to see. This one's a border point. Am I allowed to add the neighbors of, let's say, this neighbor? I don't know if there's a neighbor. Let me start with this one. Let's start with this. Is it core or border? Border. Am I allowed to add this one to our queue? Because this one is the epsilon neighborhood of a border. It should be in the epsilon neighborhood of what? A core point, so I'm allowed to add it to our queue. Okay, so I'm not allowed to add it. But I'm going to say that it's visited, so we already... Is it that one? How about this one? Core or core? Now, am I allowed to add this? Yes. So now we add it. We're going to go over all of these. How about this one? This one is a core or border? Hard to see. 1, 2, 3, 4, 5. So am I allowed to add these? Do I have any unvisited data point in our queue?
Yeah.
Which one? Oh, you're right. You got me there. How about now?
No.
No. So how many unvisited data points I have right now? No. We already...
Yeah, because that's a
You already visited this one, right? Outlier. So how many we have? 5. Let me start here. I can start from any of them randomly. Is it core or not? Yes, 5. Core. Done. How many clusters I have?
3.
How many? 2. Outliers are not part of clusters. Okay, so we have, did I need to define the number of clusters? No, it would just gave me the number of clusters. Okay. I'll call this algorithm almost deterministic. Anyone knows what this deterministic algorithm means? This one is almost deterministic. What does it mean by a deterministic algorithm? Given the same input, you'll get the same output. So why it is the case? Because we're going to have some troublesome points. Let's say if I had a point here, let me use this one. If I had a point here, if I have a point here, and if I have a point here. Okay, so if I start this algorithm, if I start it from this part, you can see that this middle point becomes a part of this cluster, right? That point which is bridging between two clusters. But if I were to start this algorithm initiated from this point, so that point becomes a part of the other. So it can switch its membership depending on where I started. So some of these data points, like especially the bridging one, okay, between two clusters can be problematic. Yes?
So is that not deterministic because we decided which side we're doing it on? Because if you choose beforehand which side you're starting on.
So let's say if I wanted to make it deterministic, absolutely deterministic, I have to say I have to have a fixed seed, random seed, which means that we know where to start. But if I didn't have this problem, even if I didn't have that problem with the random seed, it could have been a deterministic algorithm. But because we have this kind of swinging point, that can be a part of any other clusters. Okay. Good. So the other one, so you can see that we have core, border, and outliers. Okay. So these are just mainly definitions, perfect questions for, there you go. I'm telling you, perfect question for quizzes. Okay. When it comes to programming, the programming of this is quite different than these definitions, but I want to make sure that we understand them. Okay. So if Q is a core point and P is an epsilon neighbor, immediate neighbor of that core point, okay, it's an epsilon neighborhood, we call this one the relationship of Q and P are directly density reachable because in the immediate neighborhood. If Q is a core point, it's better that this graph is not complete. So maybe I should put this one 3 dots. Okay? So if Q is a core point and P2 is also a core point, there is a chain here. Is P in the epsilon neighborhood of Q? No. But through this chain, we call that Q and P are density reachable. Can I say that P and Q are density reachable? Can we say this? We don't know. What if P was a border point? Yeah, but what if it wasn't? Because we don't know the status of P. And that's why we just say that density reachable is one directional behavior. There is no symmetry here. Okay, one directional behavior. The other one is called density connected. So O is a core point. What do you think is what is the relationship between O and Q? Because they are connected through a chain. What is the relation between O and P? Density reachable. So if there is a core point, and I have density reachable here, and I have density reachable here, I call P and Q are density connected. Q and P also are density connected. So symmetrical behavior holds here. Okay, for this one, symmetrical behavior holds. Give you an example. So if I start here, these 2 points, what are their status? What is their relationship? They are, it's within the epsilon neighborhood. They are what? Directly density reachable. How about this one and the first data point, the first core point? Going from here to here.
Density reachable.
This one is density reachable through a chain of core points, okay? So let me put it here, put it here. How about now, if I have this point, these two, A and B, through O, what is the status of A and B? Because from O to B is density reachable. O to A is also, so A and B are density connected. Or B and A are density connected, doesn't matter, yes. Yes, they can be dense, they can have different status, that's okay.
So B to A is density reachable, but A and B are also density.
Yes. If we can find a chain to go from B to A, yes, we can call them density reachable. Yeah, so they can have different status here. So to give you an example, this is one of the very good visualization out there. I've been always enjoying this. So we're going to do image smiley visualization, how dbScan works. Okay, I'm using epsilon1 and mean PTS 4. So this means that where I start this algorithm. Field color means if I started from that point is a what? What type of points we have? Core, border, or outlier? Core, that's why you have a field color. Let's start it. Let's see how this algorithm works. Okay. Let's see how it works. Are we happy so far? Yes. Oh, it stopped there. Let's see what happens. Okay. Doing very good. Perfect. So, and then we have this. How many clusters so far? 2. Now 3, and now 4th. Rest of them are outliers. Good? Okay, so now I have a question. I'm going to tell you that this algorithm is very sensitive to epsilon. In fact, it's not that sensitive to mean PTS. What if I want to have less number of clusters? Should I increase the value of epsilon or should I reduce it? If I increase it, it's going to just find more points. Let's do it. What should I put for epsilon? 5? 5 is, I'm telling you, this is so sensitive. You're making it 5, okay. It doesn't even go to 5. 10, thank you so much for making it better. Okay. So let's do it this way. Uh-oh, this is happening. Okay, so are we happy with this clustering? No, you should not be happy, okay? So we're just using one color. Okay, that's not about it. Okay, so how can I have more, yes?
Can you explain exactly what epsilon is like meaning for this?
Epsilon means the radius of that search. So mean PTS is 5. This means that we're going to increase the chance of having more points, which is going to satisfy that requirement. There's a higher chance to satisfy that requirement.
Okay, so epsilon is just like
the radius. That point, the radial search, epsilon radial search. Okay. Okay, so how can I have more clusters?
Smaller epsilon.
So what value I should put in there?
0.5.
Oh boy, let's do 0.5. You're not listening, but okay. 0.5 is a lot. Let's see how many clusters we're gonna get. Uh-oh. Soon we're gonna run out of what? There you go. The min PTS, we can change it, but the effects is not that much, okay, in general. Okay, so are we understanding how this algorithm works right now? Okay. Are we happy with this? This one is over. What is this one? Is okay. If I have this epsilon value is small, it means what? I'm going to have a lot of or a lot of outliers. So we're going to just end up with having a lot of outliers. Okay. So this is a pseudocode of how this algorithm works. What is X here? In our class, X means data set. The size is n by d. Epsilon are the radius, and min PTS is the number of data points within that radius. Okay. For each unvisited point P in data set X, mark P as visited, we're going to do a region query. This region query will do what? What type of search? Down here. Return all points within the P's epsilon neighborhood. It does a radial search. Do you think it's computation friendly to do if I have 1 million points, I need to calculate the distance to all 1 million points to find out how many points are within that epsilon neighborhood. It's not very efficient. Are there better ways to do it? Yes, there are better ways that people can optimize this. Maybe they don't calculate the distance from all data points. They stop at some points because this algorithm is all about global or local. It's about local. So they don't expand the whole thing to calculation of everything. Sometimes they use something called KD3. KD3 is an algorithm which will make this distance calculation much faster. Will make it, so there are a bunch of algorithms out there to make this one more efficient. Okay, but let's say we do it, and if the size of this neighborhood, if it doesn't satisfy the condition, that data point becomes noise, outlier. If not, that data point becomes what? P becomes, if it satisfies the condition, P becomes, if P satisfies the conditions of min PDS, it becomes a core point. And now that we need to do clustering expansion. Okay, we're going to add P to our new cluster. And for all the neighbors of that core point, if P prime, that neighbor is not visited, we're going to mark it as visited. And then we're going to do a region query on that neighbor point. If that neighbor point is a core point, should I add its neighbor, its immediate neighbors to our queue? So I have a core point, and I'm checking the neighbor. If the neighbor itself is a core point, should I add this neighbor to our main database?
Yes.
Data structure, yes, we do it. And that's why we have this joined here. And the other one is if P prime is not yet member of any cluster. Outlier, is it a part of cluster outliers? No, so this means that the status of outlier can change later on. So outlier can be a part of a cluster. If it's within the epsilon neighborhood of a core point in future, it can change. Okay, any question here? Any question? Yes.
So with this algorithm, the only actual markation of the type of point is just for noise points. Like border points get processed and core points get processed through it, but the only one getting explicitly marked is noise.
Mainly the border points comes to the picture here. If it's not a core point, this means that it's a border point for this neighbor. And this part is also, you can see that this if condition is outside this if condition. This means that if a point, I know that the border outlier point is already visited, right? But if that outlier point is an epsilon neighborhood of another core point, I can change its status to be a part of that cluster, and outlier becomes what at that point? A border point. Yeah. Okay, any question? Yes.
Are outlier points added to a cluster and then you go through the clusters and see which one only has 1 point and then you don't?
So at first, if I have an outlier, it's just visited. It's not a part of any cluster, okay? But then later on, then I do a region query, and that outlier is a part of a core cluster. This means that that outlier becomes a border, so it becomes a part of that cluster. Good? Okay. Any question? No? Good. Okay. So I'm going to tell you, look at this one, how sensitive dbScan is. Going from 0.5, 0.4, disaster, right? So changing a little bit of that epsilon, look what happens. Here from 5, 3.5, 3, you can see that what happens there. Okay, so epsilon, high value means what? What's going to happen? If I have high value of epsilon, many clusters going to merge together. Okay, low value of epsilon, a lot of outliers or many clusters. Do we need to define the number of clusters in dbScan in advance? No, it will do it automatically for us. Okay, nope, we don't need it. Okay, so let's define what would be a good value for mean PTS and epsilon to start this algorithm. Okay, so mean PTS equals 1, does it make sense? Because every data point we consider it as a part of our counting. So no, please do not start dbScan with mean PTS 1. And also we don't typically do it with 2. Let's see, I'm going to draw something. Tell me if it reminds you of any algorithm. Here, 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 then this becomes a part of one cluster. This one is our hierarchical clustering. And if I draw the dendrogram as if we are cutting the whole dendrogram based on epsilon cut. So this is what we have. So we should at least start it with 3 mean PTS. Okay, rule of thumb, your mean PTS must be greater or equal than, in our class, D means what?
Number of features.
N by D. D always means number of features, dimensions. So, and if your data point is noisy, you got to use a multiplier of 2. How can you know if your data point is noisy? Data points. What's that?
Outliers.
But you haven't even started this algorithm. How are you going to know that your data points are noisy? What is the first thing that you do? Your eyes see what? You need to plot them, visualization, scatter plot. What if you have 100 dimensions? Then what do you need to do? We can't plot 100 dimensions. So what do? We reduce the dimension to 2 or 3. We don't know how to do dimensionality reduction. And hopefully that 2 or 3 dimension is a good representative of higher dimensions. So that way we can decide about what is happening there. Okay. So how about epsilon? It's very similar to elbow effect. So let's say I have this 0.1. So what I'm going to do, I'm going to calculate fourth nearest neighbor, or they call them 4NN. Why not fifth nearest neighbor? Why not 6th, or why not 7th? I'll explain it to you, but let's say we're talking about fourth nearest neighbor here. So I have this data point 1, data point 2, 3, 4, 5. What is the fourth nearest neighbors of data point 1? Which one is the fourth nearest neighbor?
5.
This is the first one, second one, third one, and fourth one. So if I put them in the same cluster, this one represents what type of mean PTS? 5 mean PTS or 4 mean PTS? 5. So fourth nearest neighbors for us means 4 plus 1 becomes that number of that mean PTS. Okay, so what I need to do for every single data, this is very time consuming by the way. For every single data point, I need to calculate the fourth nearest neighbor. Let's say for data point 1, the value is, I don't know, 7. For data point 2, the value is 3. Data point 3, the value is 8, and so on. If I have 100 data points, I need to calculate for all of them. And then if you look at this down here, this is our indices. This means that we need to just sort them in ascending order. So if I do it in ascending order, what's going to happen here? Which one is going to have the smallest fourth nearest neighbor? Which data point? If I want to sort this one based on ascending order, which data point has the lowest value for fourth nearest neighbor? This one, the lowest, the fourth nearest neighbor is 7. This one is 3. This one is 8. Okay. 2 is 3. What is the next one? 1, 7. 1 is 7. And the last one is 3, which is 8. So what I need to do, I need to start from point 2, point 1, point 3, and so on. Right, that's a sorted one. And these are the values, 3, 7, and 8. So you can see that these are the values. So what we're going to have this elbow effects. And this is going to be a good value for our epsilon. Anything further away from epsilon, over clustering or under clustering? When epsilon becomes large, am I going to have a lot of cluster or less number of cluster?
Less cluster.
So becomes under. If it's less than epsilon, that's elbow becomes over clustering. So if it's less than that, this becomes over clustering. Any question about this? Any question? Yes. Which number?
Elbow.
Yes, elbow will happen. Yeah, for sure will happen. Okay, so why not trying different one? 4 nearest neighbors means 5 mean PTS. 13 means? And 99. If I derive for all of them, you can see that the elbow effects wouldn't change that much because this algorithm is more sensitive to what? Epsilon. So you can see that it doesn't change. Even if I zoom it, you can see that the difference, the elbow is there. It really doesn't matter of how many neighboring point I'm using here. Okay, so. So when DBSCAN works well, robust to noise can detect arbitrarily shaped clusters. To a good question. One thing that DBSCAN suffers a lot is if I have density within another density. Let's look at this one. How many clusters I have here? Based on colors, come on now. 3. Okay, it doesn't understand density within another density. Okay, what I'm going to do here, I'm going to increase epsilon a little bit. How many clusters I have here? 4? Yes?
3 and outliers.
Yeah, the algorithm's saying 3.
3, and the rest of them are outliers. Be careful, okay? The rest of them are outliers. Did you say 3 or 4?
I technically did say 4, but.
But there is no technically here. Is it right or wrong answer? Okay, so if we have, and the rest of them are, there you go. Okay. Okay, so these are some, so this is our DBSCAN, like some take-home messages, so we went all of them. And this is another clustering evaluation. I did not have time to teach it in A section, which means that I should, that's what you just, that was your conclusion? Fine, I'm gonna let you go home, or not go home, go to your next class, okay? Have a good one, I'll see you next week.